people, it just trips me up. That's funny.
All right, let's try one more time. Peculiarity. Does that sound better?
100% perfect. Yeah.
Okay, now you say it. Okay, let's see which one of us says it better.
Peculiarities. There we go. Peculiarities. It needs to be a U-arity. U-arity.
Peculiarity.
There we go.
Okay, never mind. You know what? This is why you're gonna host, and I'm just gonna talk physics. All right, let's do this in 3, 2, 1.
And hello again, everybody. It's been a couple weeks since you saw us last. We're back again with another fantastic podcast on physics. Today, we're talking about string theory, which we'll get into in a moment. But again, string theory tends to be the sort of the forgotten stepchild of physics. It seems like I've heard of it. I've heard of string theory, but I've never heard people give an in-depth explanation on it. Whereas quantum computing, that seems to come up pretty often. So excited to learn more about that. Lee, welcome. How are you doing today?
Doing very well. Always love our discussions of physics. And it always seems to invoke a lot of interesting questions, both from you and some of the viewers and listeners.
Sure. Yeah, and so again, speaking of listeners, if you're new to our channel, don't forget to like or subscribe. What else should they do?
You smash that like button.
Smash the like button. Now, again, be careful if it's a new computer, maybe a little bit softly, just in case you break it. But if you feel like it, smash the like button. And again, as always, if you have any questions, leave a comment in the comment box below. And as usual, we love answering fun, interesting questions by our listeners. Those are some of the best questions we've gotten so far. Okay. So far, how about this? This might work well. Let's give a brief review of the issues we've covered. Because again, if you're watching this video for the first time and you haven't watched any of the other videos, first off, go watch the other videos. Spend your whole day. You're going to have a blast. But secondly, if for some reason you don't want to spend your whole day watching all the other videos, you can still watch this video. We'll refer to things that we've talked about before, but it's not like you need the other videos to have any idea what's going on here. So Lee, maybe you wanted to give us just a quick review of maybe the main topics we've covered so far in our podcast series.
We do work at a test prep company, Josh. Maybe we could make it a multiple choice test for our listeners, or because everybody loves standardized tests. No.
Yeah. There's one thing the world needs more of. It's more standardized tests, I think.
Yeah, right. Well, we covered a lot of the main aspects of things that are actually going to be foundational to our discussion today. So we started off with your fascination, which is you're fascinated with singularities. So we started off with gravitational singularity. So we talked a lot about gravity and what happens as very massive objects start to collapse on themselves and form gravitational singularities, which are called black holes. We then moved on to discussing the weirdness of quantum mechanics, things like how can it be a particle and a wave? How is it that there could be this, superposition of multiple states? How is it that electrons can go through two doors at once? One electron, there's just a lot of things that happen in quantum mechanics that just don't resonate with our classical minds. We did a whole segment on time, and I think that's covering time and quantum mechanics and gravity really is discussing what we observe and some of the things that we find most interesting in the world. So really thinking about the forces in nature and how we interact with them has been the main subject of our podcast.
Yeah, and one thing that's really stuck out to me with this is I remember in school when I had a physics class, it was presented as here's what an atom is, right? And then here's what's composed of an atom, and then here's some equations on gravity or things like that. But there's so many avenues of physics that almost on the final frontier, right, of human exploration. There's so many things that are just if you watch any of our videos, they're just basically on some level they're very mysterious. They're very fascinating. quantum physics. It's easy, not easy, but it's somewhat easy to kind of comprehend on an elementary level. But if you start asking questions, it just blows your mind. So very fascinating topics. One thing that I don't think has blown my mind before is string theory. Now I'm hoping that you'll be able to blow my mind today with string theory, possibly. But yeah, anything else before we dive straight into the topic today, Lee?
No, I think that's it's a pretty good background, and I think we're ready to start trying to figure out what string theory is.
Let's do it. So, like I briefly alluded to at the beginning, string theory, at least for me, again, I don't know if this is true overall, but it seems to be, it's not as elevated as other main concepts in physics. So why, maybe, I don't know, what you can take it however you want here. Like you can either describe what exactly string theory is first, or you can maybe help illustrate why we don't really hear of string theory as much as the other kind of big topics that we just discussed a moment ago.
Yeah, I think let's start with why it seems to be on why string theory is on the outskirts of our understanding, and I think that has to do with the difference between a law and a theory, right? So the gravity is not a theory. Gravity is a law. We have done enough studies that we know that if you drop an object from some height, that gravity will always pull it down. We haven't found anything that breaks that rule. So gravity is a law. Even quantum mechanics, as weird as it is, we've done enough experiments that we know particles can behave as waves and also as particles. It's weird, but it's something that's proven. So there's quantum mechanical laws.
Can I interrupt real quick? Sorry, just a kind of a technical question. So usually when a theory kind of translates into a law is when you're actually able to test it enough times. Is that kind of the transition there?
Yes.
Okay, cool.
Yeah, it's interesting. You can propose any sort of theory.
Yeah.
I think I've mentioned this before. I could propose a theory that I think neutrinos entangle information with neurons, and this is what causes people to have the same thought at the same time.
Right.
But I don't have there's no evidence to support that, and I couldn't consistently reproduce that. So it will always remain a theory until I can consistently show that it happens and then describe some mechanism by which it does. That's another important part of a law is introducing a mechanism as to why it happens.
Explanatory power, basically.
Yes.
Cool. Sorry, string theory.
Yeah. So string theory is just a theory, and it is a theory that for a lot of people who aren't familiar with it would say, well, why do we need another theory? String theory hopes to unite some impossible situations we have with our current understanding of the universe. So string theory at its core asserts that there is these tiny little undetectable strings that dictate particles and forces in the universe. So right now the current acceptance is that we have this standard model which comes out of quantum mechanics, which lists particles such as electrons and quarks and photons, and says this is how they interact. And here's a chart with their mass and their size and things like that. This turns all of that up on its head and says those aren't actually particles; those are vibrating strings. So that's a high-level view of string theory.
Sure. So the name itself, string, vibrating string too. It's interesting terminology. Is that just because it looks like a string? Like why do they term it a string in this case?
Well, again, these strings are undetectable, so it's probably just a descriptive. It's a descriptor of these particles. However, it's important to understand that they're one-dimensional strings.
Interesting.
So whereas a particle is three spatial dimensions, a string is one dimension, and the way that it vibrates causes it to exhibit properties such as an electron. So you could imagine if you have this cosmic guitar and you pluck a string a certain way. If you do one chord, it's an electron. If you do another chord, it's a quark. And if you do another chord, it's a photon. So these strings can exhibit properties of forces or of particles, depending on how these one-dimensional strings vibrate. So the string is really just a representation of something that is one-dimensional.
Okay. And then maybe a dumb question too, but do you know what it is basically, like what it's composed of? It's just
fundamental.
Fundamental. Wow.
It is a string is a string. Now there's certainly different variations of it, and you can have a broken string, you can have a closed loop string, but again, these are just, I think, descriptors for us to come to terms with a theory that, again, really kind of upends our current understanding of the universe, and that is something tangible like a particle. So yes, and kind of going back to why we need it. We need it because our two big understandings of the universe, quantum mechanics and gravity, do not agree. Once you start to look at like quantum particles, the gravity, quantum gravity, as it were, it causes what's called impossible infinities. You have these things that just don't make sense as you get smaller. So the two theories are not in agreement. That is general relativity, which is gravity, and quantum mechanics.
Okay, so those sort of are at odds with each other, and then string theory is born out of this contradiction as a way to try and resolve the contradiction.
Yep.
So how, if it were true, or maybe how does it resolve that contradiction in that case? Like, how does it attempt to bring those two together?
Yeah. So I think let's first kind of think about what the history of unification maybe is something important. So, I think as a species, we want to understand the world at which we observe things, right? So if I have a glass in my hand and it gets brighter as I get closer to the window and darker as I go away from it, I'm thinking that there's some relation there. And Isaac Newton was probably the first to come up with a unifying theory saying, hey, planets, which we thought were dictated by the heavens, actually go through the same motion as we do on Earth. He described these trajectories and saying, wow, this is unifying, these two are the same forces. Maxwell did the same thing with electricity and magnetism. We thought that they were these two different things, but they're actually two aspects of a single force, and he put those together. And then, of course, some of the big breakthroughs the next two were Einstein. He first did it with space and time, right? And thinking about special relativity, saying, hey, look, space and time are not these two distinct things. Space-time is one sort of fluid fabric. And then about a decade later, he did the same thing with general relativity and gravity, saying, hey, these forces, gravity is this force, and here's how it operates. Then after that, quantum mechanics was the next big thing that described the other forces. The other forces being, electricity and magnetism, and then the nuclear forces, which we talked about in a previous podcast.
Quick here. So, and then also, I guess, light too, right? Where light is particle and a wave. It seems like a lot of these attempts involve some kind of duality, right? Where it's like light is neither this nor that, but both at the same time. Same with the planets, like you said, connecting the heavens, the precession of the heavens with the precession of Earth itself. Like you're trying to bring together two things that seemed completely different originally.
Yeah, and again, we want to have one understanding of the world, and again, the last two big discoveries were gravity, general relativity, which works nearly perfectly, and our understanding of quantum mechanics, which also is it's a really great understanding. But when you try to combine the two, with my example with the glass, imagine that, like, as you get closer to the window, it gets brighter and brighter and brighter. And then right when you get to the window, all of a sudden it flickers or it goes dark. And you think, that's really weird. Why? Like, my theory of there being a light source behind it works perfect, except right when I'm at the window, it doesn't work. So it works everywhere, but right there. And same thing, gravity works great until you get to a quantum particle. Quantum mechanics is a great description until you try to figure out the gravity of these particles at the quantum scale. So the way that string theory gets around that is it introduces these strings. These strings allow these impossible infinities to be solved, certainly mathematically, because that's the real problem. Is when you look at quantum mechanics and you look at general relativity, you get infinities in the math, right? Which obviously does not compute with us, and it doesn't correspond to the real world. Because if you had some infinities, with the exception of black holes, if you had an infinity somewhere, we would have black holes all over the place, or we would have some major problems. Mm-hmm. So it does this by introducing 6 new dimensions. Now, these 6 dimensions are only visible to strings. So we, in the standard model, think about 4 dimensions, 3 space and 1 time. String theory says, actually, these strings kind of work in these rolled up, undetectable 6 extra dimensions. And, I guess it's like, to think that we only see like 4 dimensions, or we only see 3 spatial dimensions. It's kind of like a bird really high looking at a power line. That power line from 2,000 feet up looks like a line, right? Mm-hmm. But an ant on that power line sees it as this 3-dimensional cylinder, right? It's massive to this string, in this case, of the ant, and we're this bird seeing it from above, and it's like, we don't see these other dimensions. So
it seems kind of crazy that they had to go for, not that they had to go for, but the theory demands like 6 dimensions. That's a lot of dimensions, it seems like. Obviously, that's probably just advanced math that it had to work out that way.
Yeah, it's a mathematical construct, and that's one of the major successes of string theory. Even if string theory doesn't turn out to give us an understanding of the world, there's a lot of mathematical successes that have come out of string theory. Duality is a big thing, like as you talked about, and that's analogs and duality is something that string theory has really helped us to understand. It's advanced quantum computing, and it's advanced a number of other fields. And it's important to know that string theory is actually, there's a fracture of a few different theories. I think that there, certainly in the 90s, there was 5 competing theories, and they came up with M theory, which was an 11-dimensional theory. But one of the theories, I think, called for 26 dimensions. So, it's all of these different theories call for different ways to interact. And what they're trying to do is they're coming up with this theoretical construct to try to make sense of, like, they're solving more problems. They're trying to keep solving problems, right? They're like, we fixed this, but now there's a new problem. And, the only way to fix this is to introduce 2 more dimensions. And so this is how you end up with 20 unseen dimensions.
Yeah, you're just trying to get the math to work out, right?
Yeah.
So the dimensions themselves, though, I guess the string theory doesn't really describe what the dimensions, each dimension does or is. It's just that they exist. Is that the key thing? Or like they're trying to prove just that they exist?
No, they describe how the strings interact in these dimensions. But again, it falls out of the mathematics. These strings have to operate in these other dimensions in order to solve the infinities. But again, there's just a lot of requirements that come out of string theory. So thinking about some of the problems, it needed more dimensions. String theory does not predict or describe an expanding universe, which we know we live in. And it requires an equivalence of force particles and matter particles, and they call this supersymmetry. So you'll hear things in physics called supersymmetric pairs, which by and large is also undetectable. So, it's kind of like, telling somebody a story and saying, "Oh, you have to believe me, Josh." It's just like, I just keep saying, "Oh, well, that you can't detect that, but just trust me, this is the case." And so you're more relying on the fact that, oh, well, I can't disprove what he's saying, but now it's getting so far-fetched that, some people have given up hope that string theory will be this all-encompassing theory of everything. And this is what they're searching for. We want a theory of everything that describes the entire world in one theory.
So that makes sense, because something like the theory of relativity with Einstein, it was a theory first, and then experiments later on bore him out, right? There was data that proved that he was correct. And actually, there's still stuff that he theorized that I think is now, every couple of years or so, I'll see an article where they're like, "Oh, we finally found something else that Einstein had theorized about, and we proved it now." But string theory is kind of like Einstein, but with no results yet. Like, it's great. It looks like a lot of sense. It makes a lot of sense, I guess. In theory, it takes care of a lot of the infinities in math. But instead of the evidence, or a lot of evidence, it's more just like, we need more theory, we need more dimensions, but we can't actually prove those dimensions. But it makes sense in math, I guess, is the key thing.
Yeah, it makes sense in math, and it's interesting because when they open this framework, again, we understand a plucking of a string, right? We understand that when something vibrates, like, you can get two different sounds by plucking a string. So it's not that far removed that you could, as long as you could assert that there is this undetectable one-dimensional string, and you could say, "Oh, I see. If it oscillates at this frequency, it makes a proton. If it oscillates at this frequency, it makes an electron." Technically, a proton is made of 3 quarks, so it would be 3 strings making that. But it could also describe things. They try to describe things like wormholes, like what happens if a string gets cut and gets split in two. Maybe that's what causes the strings trying to get back together. Could be a wormhole. And so the different ways in which these strings contort and twist causes everything we know in the universe. That seems very elegant. And in fact, just so you know, most of my research on this, it stems from this book, Brian Greene's book called The Elegant Universe. Brian writes this. You don't need a physics background. Again, this was my background, because you don't take string theory. You certainly don't take it as an undergraduate, and you don't take it in graduate school unless you are specifically studying theoretical particle physics, or you're
interesting. Not even in grad school. That's fascinating.
Yeah, it's just some people might claim it's a waste of time. You should spend your time as a graduate student studying things that we've proven. And this has not been proven, though, as I've pointed out, there's been a lot of successes in terms of its mathematical. Even if they proved string theory could not be a theory of everything, they made a lot of mathematical steps forward. And they also were able to describe the entropy of a black hole. I think it was Hawking and a few others that helped move that forward in the 90s or something. So there's been a lot of great things that come out of it. But
yeah, can I pause there real quick? Going back slightly, I was thinking maybe people wouldn't fully understand why an infinity in math would be a bad thing. My assumption, correct me if I'm wrong, is that when you have formulas to describe reality, or to describe certain things or actions taking place in reality, you want them to basically resolve and be, like E equals MC squared. Did I get that right? If I got that one wrong, I just need to stop hosting. Um, but the infinity, basically, if you come to an infinity in a math equation, it's the fact that you obviously can't have an infinity in a finite universe, in a universe which is, it was created, or Big Bang, whatever you want to say, and then it's going to end at some point. And so the infinity is where things start breaking down, right? Is that a good way to describe it?
Yeah, great way to describe it, Josh. It's exactly like you stated. A mathematical infinity, there are ways of treating mathematical infinities so that you can sort of work around them. But if they're coming out of a theory, we know that's wrong, because we know there's not an infinite amount of energy in the universe. We know that it is finite at some level. It could be a really big number, but there's a difference between a really big number and infinity. And infinities generally kind of kill the rest of the equation, right? You're trying to come up with some scale, and it's like, oh, well, it's 1/2 infinity, and it's like, okay, well, that's still infinity, right?
Yeah.
Like, you just can't work with it once it sort of blows up the equation.
Right. Infinity can't really have modifiers attached to it. You can't say half infinity or near infinity. I mean, I guess you could say near infinity, but that might be a topic for another podcast.
Yeah, there's something called semi-infinite, but those are
Interesting.
mathematical treaties, and obviously when I was a kid, or you would always say, "Oh, I got infinity." And you're like, "Oh, I got infinity plus 2."
Yeah, I do remember that. That's funny. Yeah. So then, okay, so going back to string theory, one last question there, I think, about the general makeup of it. This may also seem like a weird question, but if it's a one-dimensional thing, vibration, how does it interact across so many different dimensions, if that makes sense? Like, I guess I'm kind of breaking down there if it's just one-dimensional.
Yeah, it's the way that once the string starts to vibrate or contort, it is when it exhibits properties in what we'll call the visible dimensions to us. Let's say the 3 space dimensions that we observe and the time dimensions are things that we observe. The string is sort of moving in and out of those 6 other dimensions, and as it oscillates, it's able to exhibit properties in other dimensions.
And oscillate, is that just rotation? Oscillate?
Oscillate, yeah. I mean, I guess vibrate is a better term for it. But yes, it's exhibiting some property that's allowing it to be visible in in a different dimension. Kind of like if I block the camera, you can't see me, but if I open it back up, now you can see me in a dimension in your house or something.
Okay. And then the vibration, another question, I guess, do they know what causes the vibrations, or is it just that, again, it's fundamental, right? It just vibrates, it just does that?
Yeah, I mean, I guess again, this is getting out of my direct field of study,
Sure.
but much as in the standard model and general theory of relativity, the strings interact with each other, and as they're oscillating, they'll feel each other, and that's how they interact, right? A string vibrating as an electron and a string vibrating as a quark are going to sometimes probably repulse each other at some point and then attract each other at some point. And so, again, the fact that it's a one-dimensional string oscillating is really just a mathematical construct for us to make sense up here. It's undetectable. We wouldn't have any means of being able to detect it. So there's no way of proving that it's actually a string. It could, I don't know. I guess it's tough to think about it being anything else if it's one dimensions, right? Like one dimension is just a line, and if it vibrates, it looks like an oscillating string.
Gotcha.
Yeah.
And then, okay, so going off of what you just mentioned there, not being able to ever prove it, how did they first? This is probably too technical of a question, but how did they first discover it? I guess, if that makes sense. Was it just how did they get from the infinity with the equations, it breaking down, and then thinking, okay, so the best explanation, the only thing that would make sense would be this string theory or these vibrations?
Yeah. So it was it's this repeated attempt to meld the laws of the large, which is gravity is essentially, it's what Newton first conceived as like these big heavenly bodies, right? It dictates heavenly bodies. And quantum mechanics is the laws of the very small. It's trying to reconcile both of those, and that search for saying, oh, how is it that both of these are 99% correct, but when we try to combine them, they completely fail? And so there was, I believe, there was a scientist at Caltech, Schwartz, I believe, and he was the first, I think, to publish a paper showing that string theory could sort of overcome this, again, by introducing these dimensions and saying, hey, mathematically, now we can get them to agree. And so if you can overcome that hurdle, we just need to rectify the physical description of it, right? That what doesn't work is the mathematics of those two theories, and that's what they're trying to reconcile. That's what is left unknown. And so again, it's theoretical mathematicians and physicists, kind of just doing what physicists do, is that's tinkering around with mathematics until something works, and then trying to provide a description for it. Whereas, as opposed to experimental physicists who observe something and say, God, we need a model to figure out how this works. This was sort of the reverse. Hey, this works. How do we, first of all, can we detect it? And then how could this replace our current description so that it makes sense to us?
Yeah, that seems like an interesting kind of dichotomy in physics, which probably happens to a lot of fields, but the experiments or the experiential physicists who are observing things and attempting this, and then versus the theoretical, so you start in the head and see if you can work your way backwards. Is that how it usually breaks down with physicists, kind of along those lines? Yeah.
Some of the best experiments, I was very lucky to have truly, when I worked at Lawrence Livermore Lab, there was just truly brilliant experimental physicists who had enough theoretical understanding, and enough theoretical physicists who had enough experimental understanding that they worked well together. But it's not uncommon for a theoretical physicist to say, oh, you can't detect that. And the experimental physicist says, well, but I did. And he's like, oh, but it's not possible. It's just like, I mean, look, unless I read the detector wrong, I did it 100 times. This is what's happening. And so, again, the experimental physicists are just trying to detect things that are happening, usually extreme phenomena. We like to study extreme phenomena because very interesting things happen there. It can be difficult to model extreme phenomenon. Things like I studied very short time scales. It's very hard to set up experiments for very short time scales, and it's very hard to model them without having massive supercomputers. So
yeah, it's funny when you're talking about the theoretical physicists, it almost sounds like they're like the hipsters of the physics world, where if it becomes proven and cool, like everyone's doing it, then they no longer like want to do it anymore. Like once you start observing it, you're like, oh shoot, I'm no longer in theory anymore. It's not cool.
Well, but and again, you need them both, because if you detect something, in order to so the way that publications work, if you want to publish in a journal, at least an elite journal, if you ever want to publish in Nature, you need to detect it, have some backup of that detection, and then have some sort of framework for this is the mechanism, right? Just detecting it, you could end up in a journal like a Journal of Experimental Physics, which it's not bad to be in there, but in terms of the hierarchy of it, you want to have both of those, the observation and the theoretical backing, which gives you some mechanism as to why it's happening.
If you want to go mainstream and sell out as a physicist, you have to combine both. I'm trying to create more drama in the physics world. Okay, so so let's go back to something you mentioned earlier. I think that will help set up the last part of this podcast. Like you mentioned, you don't even really study string theory even in graduate school unless your field is particularly focused on that. So again, that seems like in a very short amount of time, string theory went from potentially describing everything, bringing these two things together, to kind of spiraling off into the theoretical, if that makes sense. Is it dead, or is it a dead theory, or is there any kind of, like, is there any hope that it's going to, obviously there'll be some hope, but is there a decent amount of hope that it could be proven, or will just kind of be like this narrow discipline of physics for the foreseeable future?
Well, again, it's we're in a search for a theory of everything, and we we need both aspects of. We need to do more experiments. We need to test what string theory has put forward, and we also need things like Schwartz did, where it's like just keep exploring what is theoretically possible in the mathematics, and then that helps it helps experimenters know what to look for, and then when experimenters make a discovery, it gives theorists an idea of where to start from. So it's that interplay. And I don't, again, I'm not completely up to date on it, but string theory is not dead. There may be a big discovery that says, actually we had it right. We don't need 6 dimensions. We need 100. But if you do 100, it's perfect. Or you need 108, or maybe we can do it with 2, right? Maybe they're trying to do something more simplistic. So they're modeling it, and maybe they come up with a new description, or maybe they modify it. But there is still research. They are still testing for what's called super symmetric pairs in string theory. That's another thing that string theory requires. So they are still looking for, if they find super symmetric signatures, they'll say, oh great, that's something else for string theory, and they'll probably generate grant money, and people would start doing more theoretical understanding of it. And again, theoretical physicists are still exploring this theory of everything, and string theory was a contender, and with modification might still be one.
Sure. The super symmetrical pairs, I mean, it sounds somewhat I mean, obviously I know nothing, but it sounds somewhat similar to, superposition and entangled pairs. But I assume there's really no connection between those two types of concepts in that case.
No, not in that much. No,
Okay.
basically supersymmetry is just a relationship between two classes of elementary particles. So basically, things fall under two categories. They're either fermions or they are bosons. And those two distinctions have to do with this intrinsic property called spin, which isn't actually spin as we know it. It's something that we call spin. We also label quarks as, like, there's a color of them, but it's not like, oh, that's a blue quark. It's like, no, it's not actually blue. It's just a intrinsic property of it. So this basically just says we have to have a relationship between those two. It's for the mathematics to work. So a lot of this is, hey, in order for string theory to be correct, we need supersymmetry. But some of these particles are only around for fractions of a second. And so this is why the Large Hadron Collider in CERN, the thing is, what is it, 20 miles long? It's
crazy.
Biggest accelerator in the world. They need these massive detectors, very fast timescales, because when you smash together particles, they will make other particles, and they're trying to put enough energy so that they can detect these certain types of particles, right? They're going through this list and saying, what will it take to detect this? What will it take to detect this? And if they create those, the environment necessary to see that particle, and that particle never shows up, then that's maybe a nail in the coffin saying, something is wrong with this theory, right? There is no supersymmetric pair for this. So either modify the theory or let's kill it.
It will be dead at that point.
Yeah.
Yeah, that reminds me of, because in my undergrad and in my master's, I majored in political theory. So it's political science, but it's the theory of politics. Like, why does politics exist? What are different forms of politics? And I most of my class is centered around just like analyzing different systems of politics, and there were many that were dead that no longer worked, or at least no one did anymore. There are many that people do now and were terrible, but we studied all of them, and I found that very helpful. Yeah, I just wonder with physics why. I mean, I get why, but the fact that it seems like all students are kind of geared towards like grants and experiments without the theory. Like I agree. I'm more on the theory side, even though I made fun of them calling them hipsters. I'm more of like, we need some weird, even if string theory technically is dead, I assume it was still very helpful for all these things that we discovered. And we'll bring up a moment like what are some cool things that came out of it. But yeah, it's just interesting that like even in grad school, you're not going to get exposed to it unless you are definitely going to study it, if that makes sense.
Yeah, it is. It's interesting too to think about, things like political theory, right? There's, you're trying to reconcile maybe two different. If you have a two-party system, how do you reconcile 2 points of view, right? We live in a world where we have a two-party system, and they have two different views. At some point, are they still observing the same? They're observing the same event with two completely different views on it. So I have never studied political science, so that is that's much harder for me. I much prefer to study supersymmetry than.
Well, it's funny. I mean, it always amazes me how similar the mode of thinking is between disciplines, because I mean, in politics, one huge thing is always, like in theory, is always you want that unifying system that will create, that everyone can be fine with, and will create, utopia on Earth. That's a big thing in politics. Everyone just wants to get to utopia. It'll be cool. We don't have to worry about anything anymore. So you get systems like, communism or fascism, which are just, or totalitarianism, which are just complete and utter dedication to one thing, because it's like we need one answer. This is our answer. But then obviously it breaks down when you exclude problems with the theory, if that makes sense. And I mean, I'll stop with politics in a moment, but it's funny to compare that with the American system of government, the Constitution, because in my opinion, again, the reason it worked so well for a long time was because they didn't try to be perfect. They didn't try to create a perfect system that would make humans themselves perfect. It was just like, well, here's what we know about humans. They're not great, they're cool, but if there's one thing you know about politics and history, it's that like people like to destroy each other eventually. So what are humans? And then let's create a system that would best kind of temper the I guess evil of humans too. It's just funny to compare those two different. It's the same thing across disciplines. I'm telling you, the theory of everything's always there.
It is. I think one thing that comes up in the theory of everything that physicists and mathematicians state is they're looking for harmony. Right? The same as you're looking for. You want to create a system that creates harmony so that human beings don't kill each other. The analog in physics is you want to create harmony so that equations don't kill each other and don't blow things up, right? This is the infinities. That's what they're doing. It's equations killing each other. So
yeah, you're exactly right. Yeah, it's funny because it is basically the same. Obviously, it's a lot different because you're dealing with humans and the real, like, not the physics doesn't deal with the real world, but humans are ridiculously complex. But yeah, it's the same. That unification theory is always there. It's funny, no matter what you're looking at. All right. Well, speaking of that, string theory. Are there any? Okay, let me see if we were discussing this word before the podcast. You want to do it, Lee? You want to do it?
Are there any peculiarities?
Very good. That came out of string theory. Are there any peculiarities? We could not say that word. If you're listening, try and say it out loud. I think you're probably not going to get it right the first time.
Say it 5 times fast and see if it doesn't sound weird in your head. Josh and I tried it about a dozen times, and it didn't ever really sound right. So we'll say abnormalities or interesting things that came out of string theory. So
yeah, it's funny if you're watching this podcast and you think like before the podcast, Lee and Josh are like poring over the data and interesting topics to talk about and like putting the research in. Now, most of the time, just trying to figure out how to say the word peculiarities. And once we figured it out, it was like, yeah, we did it. Let's start the podcast. We're in. All right. So string theory itself, what are some abnormalities that came out of it that stick out to you, I guess?
Well, it's interesting because physics is a small world, and me only spending, I guess, spending about a decade in experimental physics. I was lucky enough to work with a lot of brilliant people, and one of those people was Sylvester Gates. He goes by Jim Gates. He was at University of Maryland when I started there, and I was a TA for him. And he is a world-renowned theoretical physicist. He's been in they put him in commercials. I think he was in like a Aflac commercial or something.
That's
He probably would never remember me, but he allegedly made a discovery that caused Neil deGrasse Tyson to just be completely shocked, right? He's like, I gotta sit down for this.
Wow.
And what he told him, or allegedly, what he did tell him, that the alleged part is whether or not it made him sit down. What he told him is that as Jim Gates was looking through string theory, he made this really odd discovery that it looks to be computer code embedded in the equations of string theory. Those equations that describe the fundamental particles, he found what looked like error correcting codes. And these, the same sort of codes that programmers use to make sure that when a code gets delivered, like for your web browser, probably a sophisticated error correcting code is you type in something wrong and Google says, did you mean this? Or, in some ways it'll just fix it for you. It's like, oh, you actually misspelled cancellation. So I think you meant this. But there's ways that error correcting code can happen when massive code bases are running, and one of the codes, runs into some sort of syntax error, and it says, oh, that happened because of this earlier operation. And so just fix this earlier operation, and now the code can run through. He found that same type of error correcting code embedded in string theory.
That sounds crazy. I mean, not crazy, but very radical, I guess you could say. Man, so
what would that mean, right?
Yeah,
What if at the core of theories that governs the world in which we see, if there is error correcting code, is that chance, or is there some sort of code running behind the scenes? Which brings me to the thing I am the most fascinated with in the entire world, maybe besides Jeeps and Legos, and that
and your wife.
And my wife, of course.
I'm just kidding. Right. I did throw you under the bus there.
She's kind of the de facto.
She's just assumed. It's always assumed.
Let's just start with that assumption. Given the fact that my wife is always the most amazing thing, outside of that, simulation argument, right? What if we were living in a simulation and there was no way for us to, there was no detectable way for us to know that? Or is there?
Did the simulation theory, was it borne out a lot to do with that discovery of the correct, or is it already in place and this is a helpful?
Josh, you're getting into our next podcast. Trust me, we are going to explore this.
Okay, I'm in.
Our heart is content. I think we could do 2 or 3 podcasts on this.
Yeah.
But for those of you who are listening and are looking forward to the next podcast, look through a guy by the name of Nick Bostrom. He's a philosopher and has friends in the science, plenty of colleagues in the scientific community. And he wrote a very fascinating paper about this concept of the simulation argument, where he asserts that we essentially are the mathematics of why we are living in a simulation. So that's his paper is actually about 11 pages, but if you just look up articles, he's got books. They're on Audible. He's done plenty of interviews. Very fascinating guy, and we are going to dive very deep into simulation theory, simulation argument, and what if we are living in a simulation?
Yeah, I mean, that is an all-time teaser, I think, with the error correcting codes, because I have lots of questions about that, and that might be a nice jumping off point next time for our podcast of thinking more about what that means. Because yeah, it's crazy if you discovered that, and that would lead somewhat nicely to something like a simulation. Well, I'm looking forward to that. Before then, we sign off in anticipation of our next podcast or many podcasts. Are there any other kind of final things you want to say about string theory to put a bow on that topic?
No, I think just if you're interested in, if you're watching this podcast, you're obviously fascinated by the world in physics, just as Josh and myself are. And so, don't be afraid of books like this. When they're written by physicists, and they're Pulitzer Prize winning, and they're New York Times bestsellers. They usually leave out all of the boring stuff and the mathematics of it, and just talk about the interesting applications of it. And again, it's even though it's just a theory, it gives you another way to look at the universe. And I think, as Josh mentioned, one thing that you do really well, Josh, is you create these analogs, right? How could you connect string theory and communism, right? But like always looking at something with a different lens and trying to put a different perspective on it. And so I just think that is a great trait in any person. Certainly with students, develop that characteristic early on, and it'll serve you well in life.
Yeah, you're exactly right. That is one thing I cannot recommend highly enough, which is exploring a bunch of different theories, no matter what the discipline. And even, I mean, honestly, I'm a bit weird, but like, even if you already know it's wrong and it's weird, like at least just consider it. Because then, like with political theory, for instance, if I know all of the theories of what works well, then I don't necessarily like, as opposed to me like just believing in like communism, I'm just being a communist without ever exploring outside. Well, then I never know like what's breaking down in my theory, if that makes sense.
Right.
And that's crucial for, obviously for academia, but also just for life in general. You need to continue to be open to change and how that may change your own mental framework. Excellent. Well, this has been a great podcast. I've learned a lot about string theory, Lee. Thank you very much for all of this information. And thanks to all of our listeners for watching or listening. As usual, if you haven't smashed that like button yet, you got to do it. You just got to do it. It feels great too. Just try it out. As usual, we'll follow up this podcast with a live podcast to kind of cover questions you may have. So probably next couple of weeks or so, Lee, at some point.
Yes.
Cool. And then let's see, anything else? Yeah, I mean, besides that, again, thanks so much for watching. String theory is over. We're on to the meat of physics, the fun, fascinating parts of it. So stay tuned for these next series of podcasts, which I think will be very fun. Don't want to spoil it, but yes, I'm looking forward to it.
Best yet, dare I say.
Wow. All right. High hopes, but I think they'll bear out. All right, everyone. Thanks for watching. Enjoy the rest of your day. We'll see you soon.
Thanks. All right. One more time, Josh. Peculiarity.
Peculiarity.
Nice.
The key is that U and arity, it breaks down